Have you ever looked at a chemistry lab and thought it looks kind of like a treasure chest? You see these brilliant gem-like colors, deep blues, vibrant greens, rich yellows. Well, that's not just for show. There's a secret to all that chemical artistry. And today, we're going to pull back the curtain and figure it all out. So let's just dive right in. The big question is, what's giving these compounds their absolutely stunning colors? I promise you, it's not random, and it's definitely not magic. It's all because of this really fascinating process that's happening at the atomic level. And by the end of this, you are going to understand it completely. So what is the secret? Well, it all boils down to this one key idea, the d-d electronic transition. Now, what does that mean? Imagine you have a central metal atom, right? It gets surrounded by other molecules, which we call ligands. Now, these ligands actually cause the atom's outer electron shells, these things called d-orbitals, to split into different energy levels. So when light comes in and hits the compound, an electron can absorb a tiny packet of light, a photon, and use that energy to jump from a lower level to a higher one. That tiny little leap, that's the source of all the color. Okay, but before we get into why we see different colors, we have to talk about the one absolute non-negotiable rule. This rule determines if a compound can even have color in the first place. This is the very first thing you always have to check. And here it is, the golden rule. For that d-d transition to happen, that little electron jump, the central metal needs two things. It needs electrons that are able to jump, and it needs an empty spot for them to land in. That means its d orbitals have to be partially filled. So here's the bottom line. Compounds with the d1 to a d9 electron configuration, they can be colored. Why? Because they've got both the electrons ready to jump and the open spaces for them to land. But what about d0 or d10? Well, in a d0 setup, there are no d electrons to make the jump. And in a d10 configuration, the d orbitals are totally full. There's no room for an electron to go anywhere. No jump means no color. It's really that simple. And this is a classic exam trap, especially for something like the CUET. They'll throw ions at you like titanium-4 or zinc-2. Because these guys have either totally empty or completely full d orbitals, any compound they form has to be colorless. So if you spot a complex with one of these metals, you know the answer right away. Don't let them trick you. Okay, so let's say a compound has those partially filled d orbitals. It can be colored. But what color is it going to be? Well, let's move on to our first factor and see how this all builds up, the identity of the central metal ion itself. Just look at the difference here. This slide shows it perfectly. We've got the exact same molecules surrounding the center, 6 water molecules. The only thing we're changing is the central metal, swapping copper for nickel. And just like that, the color completely flips from blue to green. That's because each metal has its own unique pull on its electrons, which creates a different sized energy gap for that d-d jump. All right, we've seen how the metal itself is crucial. But what happens if we take the very same metal and just change its charge? Well, that brings us to our second factor, the oxidation state. And it turns out this has a massive impact on the final color we see. Here's the basic idea. A higher positive charge on that central metal acts like a stronger magnet, and it pulls the surrounding ligands in closer. When they get closer, they cause a bigger split, a larger energy gap between the d orbitals. And a bigger gap means it's going to take a higher energy photon of light to make that electron jump. And check out this fantastic example with iron. With a +2 charge, the complex is a pale green. But if you increase that charge to +3, bam! The color shifts dramatically to a kind of yellowy brown. This is a super important rule to remember. Same metal, same ligand, but a different oxidation state is always going to mean a different color. So, we've seen how the metal and its charge are key, but now we come to the factor that, honestly, often has the biggest impact of all, the identity of the ligands themselves, those molecules that are actually attached to the metal. To really understand the power of these ligands, chemists use something called the spectrochemical series. It sounds fancy, but it's basically just a ranked list. It's a power ranking that tells us how good a particular ligand is at splitting those d orbitals. Some ligands cause just a little split, while others cause a massive one. So let's look at a simplified version here. On one end, you've got your weak field ligands, like the halides. They cause only a small energy split. On the other end, you've got the strong field ligands, the heavy hitters, like ammonia and cyanide. They cause a really large energy split. And this difference in the energy gap is what directly dictates the color of light that compound is going to absorb. Okay, so we know that different ligands change the size of the energy gap, which changes the color of light that gets absorbed. But how does that lead to the color we actually see? Well, this is the final crucial piece of the puzzle. The key is that the color we see isn't the color that's absorbed. It's whatever's left over. Let's walk through it step by step. First, white light, which has all the colors of the rainbow, shines on the compound. The compound then absorbs only the color of light that has the exact amount of energy needed for its d transition. So for example, if it absorbs orange light, all the other colors, red, yellow, green, blue, violet, they just pass through or reflect off. Our eyes collect all that remaining light and our brain processes it as the complementary color. In this case, the complement to orange is a beautiful blue. Pretty cool, right? Okay, wow. We've covered a lot of ground. So let's distill all of this down into a really clear, concise toolkit that you can use, especially if you're studying for an exam like the CUET. Think of this as your cheat sheet. Let's boil it all down. First, the golden rule. For color to even be possible, you need a D1 to D9 configuration, no exceptions. Second, remember the color comes from that electron jump inside the metal, not from the ligand itself. Third, if you change the metal's oxidation state, you are absolutely going to change the color. And finally, here's the big shortcut. Strong field ligands create a big energy gap. That means they absorb high energy light, like blue or violet, and what we end up seeing is its low energy complement, like yellow or orange. So the next time you see a brilliantly colored chemical, you'll know exactly what's going on inside. You'll practically see those electrons jumping, the photons being absorbed, and the elegant physics of d-orbitals playing out right in front of you. You now have the rules, not just to understand chemical color, but maybe even to start predicting it. Thanks for tuning in.